Okay, let's proceed. Okay. I hope I'm online, the thing, because I've been just talking. So yeah, I haven't disconnected yet my network. Okay,
no,
cool.
No.
Okay, so normally it's often useful to go through a history of topology and these things, but I won't do that because we don't have time for that. But I recommend you to, here's a URL, this a brief history of topology by the University of St. Andrews. It goes very in detail, the genesis of topology, with the Euler, the Königsberg bridge problem that he was trying to solve. It goes on through all that, blah, 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 to Poincaré, to, Hausdorff and all these characters that shaped the birth of the subject of topology. So we won't do that. We will dive straight into it. But those of you who are interested in history of a thing, I really recommend you to go here and read a little bit of a history of the subject. Okay. Okay. So let's go. Here's the first definition. Okay. For those of you, especially the newbies to this, do not panic. I will try to decode this step by step to you. So do not panic. So suppose that X is let X be a non-empty set, okay? So a topology on X is a collection of subsets that I denoted T or calligraph T or whatever it was. I don't even know what's this called. It's a subset of the power set, So set theory 101, the power set is a set of all subsets of X, okay? And it's not just any collection. It's a collection that satisfies these three conditions, okay? So the first condition is that the empty set is in the collection, is in T. And the set itself is also in T, okay? So this is the first condition that this thing has to satisfy in order to be, classed as a topology, okay? So if I give you a T and tell you, give me $10 for it, you have to make sure that the empty set and X is in the collection. Otherwise, I've cheated on you, okay? The second condition is that if you have a finite collection, let's call them like O1, O2 to OK, then the intersection of these elements of T have to lie in T also, okay? So in other words, this is telling us that T is closed under a finite intersection, okay? The third condition is that if you have a collection, this is indexed like, by an arbitrary set I, this could be an infinite set, okay? This can even be a countable and uncountable set, okay? Then the union of all the elements of this collection, this indexed subsets of T, has to lie in T also, okay? So if it satisfies these three conditions, then T is called a topology on X, okay? And the pair X together with T is called a topological space. This is it. As you can see, it's very abstract, At this stage, especially the newbies, some of you never who have read the topic of topology through like popular books, with things like, donuts, cups and spheres and these things. At this first sight, this has nothing to do with that. You're like, what is this? Yeah, but those things, those objects actually satisfy this. They are also topological spaces. In fact, those objects are actually topological manifolds. We'll see later how that, why that's the case. Okay, you'll only see that when we get to the metric topology section. Okay, so the pair is called a topological space, and it's also by convention. Whenever this topology is understood, there's no need to be writing the pair. We'll just write X and call it a topological space. But for us, we will for some time keep using this because we are working in the abstract. There is no concrete topology. So we'll just for fun, we'll just keep writing like this for, for the next couple of lectures. I will use this until we get to manifolds, and then we can get rid of this thing, because then we are working on concrete stuff. We have like a concrete topology. Okay. And another thing is we'll call the elements of X as points. Okay. So that's it really. So this is what topology is. A topology is a collection, is a sub-collection of the power set of X that satisfies these three conditions. If anything that, if it fails to satisfy it, then it's not a topology. So it has to, okay? So the question is, the simple question is if we make T equals to the power set itself, is it a topology on X? Let me check the chat. Come on. There's a question here. I will address that on the thing at the end after. Let's see first. Is this a topology on X, the power set? If we take the T to be the entire, let's look at it. You know, so the power set is a collection, is the set. Is a collection of all subsets of X. So definitely X is a subset of itself, then X is also there, right? Okay. And the empty set is certainly there, because remember, the empty set is a subset of any set. This is set theory 101, or naive set theory 101, okay? So it satisfies those conditions, this first condition, certainly, right? And then if you pick any finite collection of the power set, then surely the intersection of that collection of the power set will also lie on the power set, right? Okay. So it satisfies that. The same with the thing. So this is indeed a topology. Okay. So this is called the discrete topology. This is actually the largest topology on X. For any set, this is the largest. So this is the most extreme case, the largest topology that you can have on X. Obviously, as you will see, this is actually this is useless. This is not what you normally use in practice. You use you know. Anyway, we'll see. So what about this one? This is simple. Come on, guys. You know, what if we make T to be the collection made of empty set and X itself? Is that a topology? Come on, be brave on the chat, please. Yes or no? Just look at the thing, you know. Well, first of all, it satisfies this, right? Trivially, right? Because the empty set is surely there, and X is also surely there, right? Come on, guys. Yes. Who says no? Can anyone, because if you struggle with these examples, then you will probably struggle more. So I just want to make sure that no one is not left behind before I move on to the next one. Do we have anyone who is struggling to understand why this is a topology, why this is also a topology? Okay, cool. So it seems no one is struggling. That's okay. So let's actually see more other toy examples, and then the challenge for you. Okay, so let's first of all, sorry for the font. Maybe it's too small. So is this well visible for you at least? Because can you see the examples?
Yes. Yeah, I can.
Okay, cool. So guys, let's X be this set made of beta 1, beta 2, beta 3. And now the question is, if T is constructed like this, you know, containing the empty set, the X, you know, so therefore it satisfies the first condition of topology, plus this subset beta 1 and then beta 1, beta 2. The question is this a topology? Does it, well, first of all, does it satisfy it satisfies the first condition for sure. The question is then, does it satisfy the other? For example, if you take the intersection of any of them, finite, like obviously this is a finite set, so therefore if you take an intersection between them, will the result be still in T? And also the same with the union. Okay? Is this a topology? Who thinks it's a topology? Just on the chat. Come on, guys. Don't feel shy. Even if you get it wrong, it's fine. It's okay. That's why we are here for, right? And no one will see this this chat anyway. It will be disabled later, so don't worry. Who thinks T is a topology? Well, okay, I will claim that it's a topology. Okay, if I made typos, maybe you will correct me later. Okay. Okay, so T is a topology indeed. You know, I claim that it satisfies, well, at least you know the first condition. This is easy, right? The empty set and the X itself is there. Okay. Now, what about this one? Is this a topology? If we consider X to be like the same set, is this also a topology on X? I will help you. Okay, for example, take the union of this and this. Will the result be on the thing in T? Come on, guys. Yes, it's this is not a topology. Indeed, it fails in here. Okay. If you are struggling with this, it's okay. It's fine. This is normally like you know, it's you know, it's very abstract, and these things, you know, take your time, you know, to go through the definition and you know, go through the example, because if you are struggling with this, then you will probably struggle with the next few sessions. Okay. This one here, so when X, this is a topology indeed. This example here, this is called Sierpinski topology. And the question is, I want to answer this. This is like a challenge for you, okay? If X is the same, but now the topology is like you know, defined like this. So the only difference is that you have, instead of one, you know, the subset with one on it is you have a 0. Is this a topology? Okay, I'll leave that as a challenge. Yeah. Anyway, one thing that you should notice, obviously, this is like we are talking about finite sets. Okay. For us, finite set, here's an interesting table. You know, in terms of the cardinality meaning the number of elements of X. Okay. So if X has one element, there's only one possible topology, which is the trivial topology. This guy here. Okay. This is the only possible topology. I'm sorry. Now, when X has 2 elements, you have 4 possible options for the topology. When equals 3, you have 29 possible topologies. When it has 4 elements, you already have 356. I hope I got it right. Possible topologies. You get the picture, right? So this the number increases, you know, massive, astronomically, right? So, you know, one of the questions you will ask yourself, you know, which topology do you pick? Okay, which topology you pick? And this is certainly an interesting question. At this stage, that's probably it's not worth asking. Once we get to the manifold section, nevertheless, it will be interesting to ask this question. Okay, and for those guys interested in combinatorics and this type of stuff, the question is, can you, this is a challenge for you, go and scratch your head. Can you find a generalized formula for this? You know, so given, if I give you N and say, here's the cardinality of X, you know, how many topologies, how many possible topologies of that are possible in X? So try to think about it. Okay. And now this is a side note. This is not something that you can just close your ears. You don't have to think. This is called Zariski topology. So it's defined like this. It contains the empty set, and it contains all the subsets of X whose complement is finite. Okay, this is a very important topology in algebraic geometry. In fact, it helped build the foundation of the topic. Okay, so just to say, like with the abstract, with the very abstract thing, you can define, you can construct some very interesting stuff that have a massive impact in the other branches of mathematics. I'll comment more on this Zariski stuff, because originally these axioms of topology were not the way people like Hausdorff stated them. I'll comment on that. That's okay, but please go back to these examples, these basic stuff. Go back to the definition. Look at it. And try to understand. Try to get grasp of this thing. At the moment, it's very abstract and boring. I understand. Especially what I ask you, especially those of you who are coming from like you have read the popular books and these things where they show you all these the donuts, the sphere, and these things. Forget that for the time being. We will get to those in the thing. Because if you're trying to connect this abstract stuff with those things, you will not succeed at this stage. That will come when we get to the metric topology bits of the course. Okay, so don't worry, just take it. As I was saying, this is why I was saying, take the abstraction one step at a time. Okay, so okay, so that's the definition of topology and the topological spaces, and these are like the two examples. Okay. So now, one thing I forgot to mention in here, the elements of the topology are called open sets. Okay, they're called open sets. When we get to the metric topology section, you might actually see the reason, or possible hint to why this to why this abstraction, why they are called open sets in the first place. So it will give you a hint why the same. But for the time being, let's just call it. They are called open sets. Okay. Not for the time being. They are always called the open set. What I mean is the motivation for this when we get to the metric topology. Okay, so we have open sets. Well, some of you might be thinking, what about closed sets? So a subset of X is closed in respect to the topology, if the complement of A is a member of the topology. Okay, in other words, if the complement of A in X is open set. Okay, in respect to the topology. So this already telling you that if this T, you have different topology, A might be closed or might not be closed. Okay, so it all depends on the topology, on your pick. Okay, so the question is X a closed set in respect to the topology T? Come on, guys. If you set theory 101, if you take the complement of X over itself, what do you get? Is it on the topology? So how is that allowed? Yes, it is, right? So X is closed. What about the empty set? Come on, guys. If you take the complement of the empty set, this is set theory 101. This is why I was recommending that you have to review set theory. The thing, I'll put that on this description and the stuff for those of you. Maybe in the first session, you go review set theory 101 stuff, and then you will be able to follow. Otherwise, you will definitely struggle. Okay, so is the empty set? I want someone brave, not just Soham, please, on the chat. Is the empty set part of the topology, please? I mean, is the empty set closed? Come on, who wants to be brave? Who's Come on. Don't be shy. Okay, everyone is shy. That's fine. Okay. So, okay, I will claim the answer is yes. Okay. What about this? If we put x again, like beta 1, beta 2, and we consider this topology is a subset A that's consisting only of the point beta 3, is it closed in respect to this topology? In other words, if you remove beta 3 from X, the result of removing beta 3, is that in the topology? Okay, I'll leave this as a homework because otherwise I will be saying everything just myself, right? So I'll leave this as a homework, okay? And also if A is equals to this, to beta 2, okay? And feel free on the thing, for those of you the thing, you can ping on the on Discord. But I leave this as a thing. I'll stop answering because you really need to think hard for you to be able to see this, okay? And then here's a proposition, okay? First of all, for those of you who are joining, it is a normal. It's like how do you say? It's normally mathematicians, they reserve the word theorem to something very, very important. So instead, for like easy stuff, we call them like propositions, okay? So proposition is also a theorem. Okay, someone just someone is on Discord. Okay, just give me a second. I think I've got a notification. Is everyone chatting on Discord instead of the thing?
No, they are replying here. Maybe you are not able to see them.
Okay. I do not. I cannot see. Can you see the answers?
Yes, I can.
Okay.
I can.
Wow. Somehow I'm not able to see the answers on the chat. I don't know why.
I guess if you're full screen, you might not be able to see that.
No, I can see on the thing on the chat. Like I can see it on the side, but I don't see the new messages coming in. The last message I see is coming from someone a community member, Brendan Perry, saying yes. But I think this question was to do.
No.
Yeah, go ahead, please.
The last message on the chat is from Amir, saying that
okay.
he's indeed getting here and on Discord.
Okay, I cannot see that. So sorry for that. Maybe technical glitch from from Discord. I was wondering that. Come on, nobody. The thing, this is unusual. Nobody is interacting on the chat. So maybe you keep an eye on the thing, please, Soham, for the time being.
Sure.
You see? Yeah.
Yeah.
Okay.
Yep,
so
definitely.
So anyway, I'll leave this as a home challenge for you, and also as a discussion point for those, especially the newbies. Okay. And okay, so I was saying, so I will label propositions as, they are also theorems, but they are not important. So I'll call them proposition and reserve the word theorem for more important stuff that will come later in the next couple sessions or so. Okay, so here's the first challenge, the proposition that I would like you really to try to prove, even if you don't manage to do it, but try it. Okay, so try it, and this is in particular very useful if you have like set up a group, chat amongst yourself on Discord, and try to set up like a proof session or something or whatever, especially those in the same time zone, and try to prove this stuff, before you look at there will be proofs in the textbook or whatever, and these things. And if you are struggling to understand the stuff in the textbook, also I can also provide my own version of this, but I would rather that you try first, because this is like I claim this is very easy. If you just it might be like time consuming and boring to do it, but it's you will be able to reason it, to reason through this thing. Okay. And this is very interesting, actually. Notice how closed sets behave in comparison in terms of the intersection and the union, sorry, and the intersection. Okay, whereas here the union is so the finite union is closed, and infinite or whatever, you know, depend whatever, it could be even an uncountable indexing of the closed sets. Their union is also closed. So it's like the stuff of inverse, the opposite in a way. These two they switched. The open sets is the other way around for open sets, whereas closed sets is this thing. So this is very interesting. Okay, so this brings it to the thing, because normally for a newbie, you know, you look at this and say open set is opposite than closed sets. But this is not the case, huh? So be careful. There are sets, like we already seen that, for example, like X is open, but it's also closed, right? The same with the empty set, okay? So in general, you've got this. This is very important for you, okay? I hope I didn't make any mistakes, but anyway, you will be able to find it and correct me later. That's a good thing. So in general, you know, it can be a subset can be open, close, open and close, open and not close, and so on, okay? And I just another thing, just for your interest, a subset is called Clopin if it is both open and closed. So therefore, X and the empty set are Clopin. In fact, later, you will see that in there's something called connected topological space, which we will cover at a later session. The only Clopin sets, the only Clopin things on the topology are X and the empty sets. Okay, so if you don't like the fact all this stuff, you can just use connected topological spaces. Okay. And here's another challenge for you. I hope you will be able to answer. Is it true that when the topology is the power set, then every open set is Clopin? Is that true? Yeah. Anyway, look at the definition of the thing and you know, and get your answer. Okay. This is a challenge for you. Now, another notion that's very important is that of a subspace topology. You know, in fact, before I go through the definition, a lot of the notions that we will go through, this will come back again in the concrete sense when we go to metric topology. We'll come back with the concrete subspaces. You know, for the time being, this is all like abstract stuff. It might be like a little bit boring. But believe me, this is very, very important in construction. Okay, so giving a topological space and a subset of X, you can define the subspace topology as this, as the intersection between A and all the open sets in the topology. Okay, and obviously this is like you already seen that the empty set and the A are also in the topology, right? Because of this. Okay, and T satisfies the conditions of the topology for sure. If it satisfies all the finite intersection and the unions also, so it is a topology. You know, I challenge you to go and you know, check, verify that this is actually a topology. And the pair, just like similar to the pair for the topological space, this is called a subspace. I've seen some authors say subset topology, but you know, in generally you call it as a subspace. So a subspace in respect to the topological space T. So it's always in respect to the topological space, to the topology. Okay, so it's very important, you know, because the behavior of the things can change if you change the topology. Okay, you will see this more concretely as we go along in the manifold and all this stuff. Okay, so it's always very important to be contextual. You know, which topology you are considering. You know. Okay, so here's another challenge. This proposition here. Okay, This is already hinting an interesting thing. I also challenge you to try to prove this. There's an interesting link between open sets of a subspace and its underlying sets, especially when on the parent in the parent topological space. Okay, and here is also like a very interesting, well, not interesting, like a challenge for you to go and scratch your head. I'm throwing these challenges here because this forces you to go through the stuff in order to for you to really understand, take advantage of the to see the power of the abstraction that we went through. These simple definitions of a topology. Okay, because if you struggle with all this, it will be very hard as we go along, especially because this crash course is not just topology. There will be some elements of a bit of a differential geometry at some point, when we talk about charts, atlases, and these things. So it's really important that you take your time. Okay. Do we have any comment on the chat, Soham? I don't see anything, as you know. Okay, good.
No, they have been answered. So.
Okay. So here's a subspace challenge for you at home. Okay. I hope so. I consider the same, the same set X with the beta 1, beta 2, beta 3, and I consider the same topology, I believe. Okay. And now the question is, if you consider the subset A defined like this, which of the following is true? Or maybe none of them is true. Yeah, but I hope if I didn't make a mistake, there is at least one of them that's the thing. Okay, that's also good news. If if I made a mistake, then that means that you are switched on. Okay, and then go through this stuff. These other challenges. I really challenge you to go through this. This is the only way you can see the to help you get grasp of the notion of a subspace. Okay, so that's the notion of a subspace, and that's the challenge. We'll come back to all this in the concrete sense in the metric topology section. Okay, because a lot of the constructions that we will do, especially in the manifold section, will be done via the subspace. Okay, inherited from the parent topological space. So it's very important, this thing. Even though at the moment it looks boring, because obviously we are in general topology, in set theory, so there isn't much. So you already started to see why we are only spending 2 sessions with the general topology, right? Okay, so let's go. The next important notion is that of a neighborhood. I hope I spelled it correctly. I believe this is the British spelling, and our American friends probably spell it differently. I think George is our linguist. George, do you agree? Is that, or is there a typo? Yeah? Okay. So apologies for the typo. So this notion of neighborhood, so this is what mathematicians define neighborhoods. So a neighborhood is a subset of X is said to be a neighborhood of a point in X if there is an open set that's contained in N. So if N has an open set that that has P as an element. Okay, so if P is a member of the open set that's contained in N. Okay. Okay. Now, this is very important to note that by definition, N doesn't need to be in the topology. Okay, this is very abstract. But some authors, they require in their definition of neighborhood, they require N to be an open set. In that case, this is called when N is an open set, then this is called an open neighborhood of P. Okay. But some authors, they require N. I like this one because this is more abstract. It's more, it gives you more flexibility. Obviously, there's more work when you want to prove stuff on the thing. But if you're not happy with it, you can just, okay, let's define a neighborhood in the sense of, let's define it like these guys, they do in some textbooks where they require N to be an open set. Okay. It doesn't matter that much. We will come to this in the metric topology section. Actually, you will see which one is much more straightforward to use in terms of proving stuff. Say, for example, Hausdorffness, these type of things. Okay. So here's another proposition. So use this definition here to try to prove this, that A is open if and only if A is a neighborhood of all its points. Okay. And also there's another proposition here with the inclusion. So this shows you that neighborhoodness has the notion of neighborhood is has some nice properties. Okay. Try to use this on the proof. This definition of neighborhood, not the one that you often see, which is assuming that N is an open set itself. Now this is very important. If anything, you can just ignore everything. You cannot ignore everything because this is important. So a topological space is called Hausdorff if for any two distinct points, P1, P2, there are neighborhoods NP1. I'll label this NP1 and P2, obviously meaning that this is a neighborhood of P1 and this is a neighborhood of P2, such that their intersections is empty. Okay, so for any two distinct points in a Hausdorff space, you can always find a neighborhood that does not intercept, that don't intercept. Okay, so this is very important. This is in the early days of, actually, I think I mentioned this before, or this is what I wanted to say. In the early days of the definition of a topology, this condition was part of the definition when Hausdorff formulated the notion of topology using the language, these notions of open set stuff. Yeah, but then after some arguments amongst mathematicians, say no, you remove that, because then you are leaving room for other interesting topologies, like for example the Zariski topology. The Zariski topology is not a Hausdorff. So if we have included this separation, this is called separation axiom, it means that Zariski topology would not exist. So this is this is very, 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 very interesting in a way. This shows even in physics and most applied stuff, Hausdorff spaces are the ones that you really want. You want the Hausdorff spaces. You will see that later. That, for example, the metric space, for example. The metric induced topology, for example, is Hausdorff. Okay, so I guess you already noticed that all the popular topological objects that you encounter, they are all Hausdorff. The spheres, the donuts, the cup, all these the thing. So that's one of the reasons. Okay, and another name for this is T2. There is also T1. We won't go there. Let's just focus on this. Okay, so Hausdorff spaces are very important, as I already said, because in our case, for example, in the constructions of a manifold, we will require a topological space to be Hausdorff. Okay, so for our purposes, we are interested in Hausdorff spaces, but non-Hausdorff spaces are very important also, especially in mathematics. Like you've seen the Zariski, for example. Zariski is not Hausdorff. So it's not just the thing. So this really depends, on your use cases. For our purposes, and in most cases in physics, certainly for our purposes, in this crash course and also in the Lie theory, we will require the Hausdorffness of the topological spaces. Okay. So the question is any of the previous topological spaces, the toy stuff that we've been building, these guys, this and maybe this, the thing, are they Hausdorff? Well, just go and check, check if there are any neighborhoods, that, if they satisfy this, okay? All you have to do is to check if they satisfy the Hausdorff separation axiom condition, okay? And here's another property. I recommend you to try to again prove this, is that any subspace of a Hausdorff topological space is also Hausdorff. This is very important. So it's very nice property to have. So you always, if you start making constructions on Hausdorff, you always stays with the you stay on with the Hausdorff. Okay. So this is very important notion, And another thing, another very interesting thing, this is something that I think you can prove. If you remove a point, if you delete a point from the Hausdorff, you delete a point from a Hausdorff space, you're still not thrown out of the topology. You're still in the topology. You're still on the thing. You still have an open set. Okay, so this is very convenient. Sometimes you might want to get rid of a point because it's preventing you from doing something. For example, imagine if X is the sphere, for example. Maybe you don't like the South Pole, for instance. You want to get rid of it, for instance. Yeah. Anyway, you will see. You will see this. This will come more into play at another thing. Okay. So as I was in the next few sessions when we get to manifold stuff. Okay. And as I said already, the Zarinsky, a bit of correction. When X is infinite and T is the Zarinsky topology, then it cannot be Hausdorff. Okay, so when the X is infinite and T, okay. Okay. So that's it, really. So this brings me. I know everyone like, how is the chat? Because I cannot see it. It's like everyone is sleeping. So I promise this is the last the thing. So I recommend this test book. And as I said, I will probably not follow the thing. You'll probably see the definitions, going like a little bit different from mine. I hope not that much. In fact, I haven't opened this for some time. But Moncrief is what I recommend. And I think I already, on the GitHub repository, there's already a link on how to download this. Okay. Go through it. Just, obviously, you can be distracted and go through all the possible other stuff that you go. I would just recommend you go through the concept that we covered today. Just focus on one thing at a time. As I was saying, take the abstraction one step at a time. Just focus on the concept that we cover. Forget any other stuff for the time being, okay? However, if you want to dive deeper and more into the thing, you can go there. Actually, this book has set theoretic stuff in there. In the first few chapters, it's all about set theory. For those of you, if you are struggling with to refresh with the basics of set theory, okay? Another thing, so the slides will be available in our GitHub repository, which is this thing. And the replay of this session will be available in our YouTube channel, which has a playlist for this crash course. And as I already mentioned, we also have a Discord channel. Please, I recommend you to go there so you can connect with other people. Maybe you will, set up a study group or something to go through the stuff that we covered today and we'll be covering over the next couple sessions. You can also follow us on Twitter and LinkedIn. And feel free to share. You might have a friend who might benefit from being exposed to topology and these things. We are just getting started. So, feel free to give a shout. Okay. So now I want to give go through the poll. As I said, there's a lot of there might be a lot of you guys that these things are new to you, so maybe you need 1 week is not enough for you. So I'll give you the opportunity to decide, especially the ones online at the moment. So I'll make the poll visible. Can you all see the poll at the bottom? So the question is, when would you like the next lecture? Next week or the week after? To give you enough time, because if you get lost with the stuff that we covered, well, there's nothing I can do for you. Huh? So I'll leave it let it run there for a bit, and then I will go and see the questions. Is there any? So the first question is there any geometric explanation of this abstract definition? Well, let me go back to the thing. Actually, the good thing to start is actually to read the history of topology. In fact, you will see a lot of the problems, a lot of the stuff that led to the thing. These definitions here, by the way, before that, I'll just comment. Normally, so this is these are like axioms, right? In mathematics, you don't need to justify axioms. So a mathematician will give you the axiom, and then the idea is that can you do anything with them, right? And there are some ground rules, like the axioms should not contradict each other, right? And they should not be like you cannot deduct one axiom from the other, so they should be independent from each other in these things. Okay, so I would say there isn't really that. There is this definition. This came about with very clever people like Hausdorff, and a few other mathematicians, on what they were working on. This is because topology is a new field of mathematics, really, compared to the classical subjects like say geometry, for instance, or even algebra. So it's a relatively new field. So the stuff, this definition, this is the most abstract that these very clever people, mathematicians, came up about that they could agree with. I think the final agreement came probably in the late 40s or something. I'm actually not sure. Maybe in the history stuff, if you read it, it will show up there. Okay. So this is the thing. So there isn't really, topology is really, you actually see like there's a, people normally say like, topologists don't care. There's a difference between geometers and topologists. Topologists don't care really about, they don't care whether things are bent and all this stuff. And this, so there's a bit of there is a different thinking between the two. Okay, so I would say there is no. So to answer to your question, there is no really geometric explanation for why we should choose this stuff in the plain side, why the axioms should be like that, but rather that the subject itself came about, evolved with different problems. Some of them might have only originated originally from geometry. Okay, some of the problems. But then the subject became independent, and these are the axioms that mathematicians could agree with, that satisfy. And in fact, this abstract definition, as we go along on the thing with the metric topology, you will see a lot of the concepts that you learn in other subjects in mathematics can actually be constructed much more easily through topology. For example, the notion of continuity, for instance, that you learn in analysis. And these things, okay? So I guess we'll come back to this question at some point, and then you will see the reason to say, oh, why? Okay, I can see why the abstract definition was like that, okay? Okay, so that's a bit of a blah, blah, blah. So the other question is it got anything with the other one is, are you seeing the chat responses? No, I'm still not seeing the chat stuff, but I guess it doesn't matter at the moment. Okay. Are all the challenges marked as such in the lecture? Yes, the challenges are all there on the thing. Oh, let's see if I understand this. Are all the challenges marked as such in the thing? Do you mean if I will score them or something when you do them? Is that what George means with this question? I mean, the challenges are there, so I will be sharing the slides.
Yeah, he's asking if it's easy to find them in the slides.
Yeah, just like they are, as they are, only thing. That's how. Yeah, yes. So correct. Yeah. Okay. The other one is, has anything to do with Sierpinski fractal? Actually, I'm not sure. So maybe it might be. Yeah. Actually, one of the things that you will see, I noticed that there's the Subspace topology has applications in things like logic and these type of things. So one of the things that you will see, a lot of the language of topology becomes very handy for a lot of branches of mathematics. It becomes very easier to phrase them in topological terms to prove them. You will see that as we go along over the next couple weeks, especially when we have like the metric topology. Okay. Okay, so I think that's all the questions. Now I need to look at the poll. So it seems most people want a 2 weeks gap, which is fine. So the next session to be July the 16th, which is fine because there's a lot of things to be to cover, and I would rather wait an extra 1 week so to give you a chance of wrapping your head around the stuff that we cover, than just rushing for the next session, and then you will people get lost, and then they give up. So yeah. So if this is the case, what do you think about this, Soham? I know obviously you are not struggling, but
no, I think that's good to take it 2 weeks.
Okay. Is there anyone else on the chat? Any comments on the chat about this, about 2 weeks? Everyone happy to do this 2 weeks? So the next session to be on July the 16th.
Sounds good.
Okay, cool. So any other question that I might have missed on the chat and these things?
No, nothing.
Okay, cool. Well, in that case, I maybe should just end it here. And I look forward to seeing you on the next session. Okay. Do not feel discouraged about this. Really, this is just the beginning. As we go more into the metric topology, things start to become more familiar. However, you need this abstraction. Okay. This is how you will be able to deal with the other section, which is a manifold section. Okay. So everything here. That's why I'm. Let me go back again just before we end. That's why I will be very focused in just going through the things that you only need in order to go in each layer of this onion. Okay, so yeah, so do not feel discouraged. This is just this is how things are in mathematics, right? If you want to learn like higher mathematics, this is it really. Things start with in a very abstract manner, and then gradually you will narrow. This is what we will do, because the topological spaces that our friends like Sohan, the physicists, need are not just any topological spaces, are a very special type of topological spaces that we call manifolds. Okay, and it's not just any manifolds. There is like different type of manifolds. The type of the thing that they are interested in are the ones that have like a smooth structure. What all this means is something that we'll come across. Yeah. So yeah. So this is it. I don't want to take much of your time. I hope you enjoyed the thing. And I'll see you on the next session. I'll follow up with the thing. Yeah. So thank you so much again to our friend Sohan for taking the time and assisting us.
No worries. Thank you.
So have a good weekend, and I'll see you in 2 weeks' time. Cool.
See you all. Bye.
Bye.